Hey, welcome back to your favorite calculus class. We're going to look at applications of derivatives in this chapter, specifically extreme values of functions. We're going to review initially, but to give you an overview of this section, one of the most important applications of the derivative as this tool for finding the optimal solutions to problems. For example, based on production cost, sales revenue, how can you maximize profit, and so on. You can read some of those other ones. So we're going to start out and talk about extreme of a function, kind of go back to pre-calculus for a minute. A y value is a minimum if that value is less than or equal to any of the y values less than or equal to on that interval. Okay, whereas it'd be a maximum if it is higher, greater than, or equal to any other y value on the interval, right? And we have absolute minimums, absolute maximums, and then local minimums and maximums. So let's review some here. Let's say we have a closed interval here. Okay, we've got the closed interval, so from -1 to 2. Now, since it includes 2, it includes this point up here. Here's our maximum up here. Oops. There's our maximum because it includes that point. And here's our, in other words, the highest point on that interval. Here's our minimum, bottom of the valley there, which is defined, right? Now, if it's opened up, this opened up from -1 to 2. Now, this is not including that point, so that there's no highest point, so this is not a maximum. Because if you think about it, like we have the point on there 4.9, but there's another y value higher than that, 4.99. There's another y value even closer than that on that parabola, which is 4.999. And there's always, in other words, there's always a higher point, but there's not a highest point because this highest point's not defined. It's not on the interval. So there's no maximum. But there is a minimum on this one, right? It's right there. There's our minimum. So think about if it's open or closed and what that gives you. Here's another one. Now this is not continuous, right? And it's got this, we've got a jump there. So there's no lowest point because it's not defined right there. We do have a maximum up there though on this closed interval. Okay, so if it's the extreme value theorem says if you're on a continuous interval, okay, if this thing is continuous, whatever it looks like is continuous on a closed interval, you're gonna have a lowest point and you're gonna have a highest point, right? You're gonna have a minimum, min, and you're gonna have a max. If it's continuous on a closed interval, that's the extreme value theorem says. All right, let's look at this one here. Y equals x squared, let's look at the entire domain. Well, for the entire domain, this keeps going, so there's no highest point. We do have an absolute minimum, the lowest point on the graph. Now, if we're looking from 0, including 0, to including 2, then we have a minimum, absolute minimum, and we have an absolute maximum up there. Now, if it's a open on 0, but then closed on 2, right? So open here, but closed right here on the third one. Okay, no minimum, no min, but there is an absolute max on that. So there's a max on that interval. Now, if it's open and open, there's no absolute extrema here. Here's some more pictures. We've got a maximum, right? It's defined. We've got a minimum, right? Maximum, top of the hill. Minimum, bottom of the valley. Could be at endpoints too. This is a closed interval from A to B. So maximum there, minimum there. Looks like we've got a maximum up there, top of the valley. We've got a minimum at this endpoint right there. And then the minimum at the bottom of the valley. We've got the maximum at the closed endpoint there, at the endpoint, okay, for that closed interval. All right, so what about local minimums? These are also referred to as relative minimums or maximums. Relative means in an interval. In an interval. Okay, so for example, let's say, well, let's look at the picture we got here. For this closed interval from A to B, the absolute highest point, so the absolute maximum is right there, right? So we have an absolute max, we have an absolute minimum, the absolutely lowest point on the entire interval from A, whoops, from A, oh my gosh, what's wrong with this thing? From A, ugh, from A to B, anyways, I guess I won't draw on it. From A to B. Now, in an interval, like for example, if we were just looking between like A and E, for example, that's the highest point in that interval, just from there to there, right? So that's a local or a relative max, local or relative, okay? In this, here's a local minimum, right? In that area, right? If you were looking just in this area, for example, that's the lowest point. It's not the lowest point. We know the lowest point, the absolute minimum is over there. This is a local minimum, okay? So difference between local and 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 absolute is absolute meaning on the entire interval. Local meaning within a restricted area that you're looking, okay? So here in this graph, it has a relative max here, right? We've got a relative min here for this cubic function because we know there is no, right? This is relative or local max here. This is a relative or local min, meaning in this area, that's the lowest point. In this area, that's the highest point. But we know there's no absolute max because this thing keeps going. There's no absolute min because it keeps going. Okay. So a hill or a valley can occur in two ways. Either we have a horizontal tangent, or maybe it's at a sharp or peak point, meaning that the derivative's undefined, right? And we've talked about relative maximums and minimums. I'm not going to. Oh, and I should say the plural of that is minima for a few relative minimums, right? Or maxima for the plural for a relative maximum. All right, so find the value of the derivative at each relative maximum. Can you see how we've got this function here? It's nice and smooth, and right here at this max, can you see how the horizontal tangent, I'm not going to take the derivative and do the calculus right now because we're going to do some later with some examples, but that derivative, f prime at 3, is 0. Now right here, that we got a sharp point. F prime does not exist there. F prime equals 0. F prime at pi halves is 0. And notice at the relative minimum, F prime at 3 pi halves is 0. Okay. So these are referred to as critical numbers. If you've got a horizontal tangent, you've got a critical number at C, or if it's undefined. Now this is with a caveat here. Your authors are kind of interesting. Remember, it depends on the textbook on this. Critical numbers are always where you have a horizontal tangent, but it depends on the authors whether they consider a critical number to be where it does not exist. Your authors, Haas, in university calculus, do not consider, they only consider the critical numbers to be where you have a horizontal tangent. Just FYI for the homework. So when you're looking at that, I think it's like number 17. Remember that. Okay? All right, so critical number with most textbooks is where the derivative is 0 or where it's not differentiable. Again, your textbook considers it just to be where it's 0. And then the relative extrema will only occur at these critical numbers. Okay. And then if it's on a closed interval, it also could occur at the endpoint. So here's what we're going to do. We're going to use our calculus to find critical numbers, to find where the derivative is 0, it's undefined. And then we're going to find the value of the function, so we can see how high or low it is, the y values. And then we're going to evaluate the y values at the endpoints. Then we're going to see who's the minimums and who's the maximums. So let's do an example here. Okay, so we got f prime of, f of x equals 3x to the 4th minus 4x cubed. So first of all, what's our critical numbers? where does f prime of x equal 0, or where is it undefined? So 12 x to the third minus 12x squared. Where is the derivative 0? In other words, where's our horizontal tangent? Let me factor out a 12x squared. So we have, where does 12x squared equal 0? Where is x minus 1 equals 0? So we have a critical number at 0 and at 1. Now there's no place where the derivative is undefined. Okay, so there's no other critical numbers. So now what we're going to do is we're going to punch these into our original function, and we're going to include our endpoints. So -1 is an endpoint because the relative min-max could occur at the endpoints, -1 and 2. And it might occur where f prime is 0. Okay, we'll just have to figure that out. So we plug in -1. So f of -1, 3 times -1 to the 4th minus 4. So I'm plugging it into the original function, and we get 7. Plug in 0, we get 0. Plug 1 in, we get -1. Plug 2 in, we get 16. Okay. So we've got this fourth power where -1 we're at 7, 0, 0, 1, -1, 2 up here, clear up here at 16. I don't know exactly. Well, actually, I got a picture of this in a minute here, but it kind of is going like this, and then kind of like this. Anyways, if I was to graph it, so I say, oh, well, here's my minimum, right? There's my minimum, and here's my max. So here's my min, here's my max. Okay. So there's a little better picture of it. Got our minimum, got our maximum. Okay, so again, where could these extrema occur? On a closed interval, they can occur at the endpoints, or at a critical number, where we're defining the critical numbers to be where f prime is zero, or where f prime is undefined. Let's do some more examples here. Now, by the way, the converse is not true. In other words, the critical numbers may not necessarily produce a relative extrema. In fact, if you look back here, f prime at 0 is 0, right? But this 0, 0 point did us no good. It wasn't a min or a max. It's just a potential. So these critical numbers are just potentially extrema. Okay. All right, find the absolute max and min of the function on a given interval and graph the function. So this is g of x. This is 4 minus x squared all to the 1/2, right? So let's go ahead and find our critical numbers. So critical numbers here. G prime is 1/2, 4 minus x squared to the 1/2 minus 1, so -1/2. Chain rule, derivative of the inside. Okay, so we've got, let's see, the 2's cancel there, so I got -x over square root of 4 minus x squared. So where's this? Equals 0. Okay, well, if the top is 0, 0 over anything is 0. So where does, so -x equals 0. So x equals 0 is a critical number. And then it'll be undefined, f or g prime is undefined if this is 0, right? If my denominator is 0, that'll make g prime undefined. I can't divide by 0. So where is 4 square root of 4 minus x squared equals 0? Square both sides. Square both sides. I got 4 minus x squared equals 0. So I got x equals plus or minus 2. Okay, plus or minus 2. So when I'm thinking about this, now notice I do have a closed interval again. So -2 is an endpoint. That's a potential. Going up to 1. I've also got to check plus or minus 2. So 2's outside my domain. I'm not even going to check it. -2 is the other endpoint, and then 0 is another one that I'm going to check, and then 1. So my endpoints and my critical numbers. And then I plug them in. Let me throw -2 in. I plug -2 into the original function. So g of -2 square root of 4 minus -2 squared, square root of 0, 0. There's that point. Plug in 0, and I get square root of 4, which is 2. Plug 1 in, I get square root of 3. Okay, so this thing looks like that. Okay, so we've got it could occur. Where's our highest point here? Here's our absolute max right there. So our max is 2. It occurs, so the max is the y value. It occurs at 0, 2, right? This is our highest point, our max. Absolute max, because we've restricted the domain. It's the highest point on that interval, right? Absolute max here. And then what's our lowest point? Well, right here. Here's our min. Our min is the y value there, 0. It occurs at -2, 0. Okay, so when you say the max is this and the max is that, it's the functional value, right? And then you can name where the location is. All right, how about this one here? Let's find our critical numbers. H prime of x, 1 over x plus 1, derivative of x plus 1, which is just 1, chain rule on that. Where is this undefined? First of all, where is it? 0? Well, there's no x value that causes this to be 0, but we can have it be undefined. So we have this critical number of -1 we got to check out, and then we're going to plug in our endpoints. -1, whoops, is outside our interval. We're only going from 0 to 3. So plug 0 into the original function. And by the way, think about that. If we'd have thrown -1 in, it's not even defined in the natural log. Right? So anyways, throw 0 in. 0 plus 1 is 1. Natural log of 1 is 0. Throw 3 into the original, ln of 4. So here's our min. Here's our max. Got a picture of it right here. Here's our max. Here's our min. Okay, let's close the interval. All right, so first derivative theorem says if f has a local max or min at an interior point C of its domain, and if f prime is defined as C, then f prime C equals 0. Thank you so much for listening. We'll see you guys next time.